Okay, yeah, welcome back. So we are deciding whether or not we want to continue and do more board work for the second half or jump onto the computer. I suspect we're going to do actually a little bit of both. But to determine this, what we lean toward, I took a poll about two questions that are important for today. The first is, do you want to do board work or do you want to do computer work? And the second one is, do you like cats? Okay. And this is the data that we came up with. Okay, so each of these cats and board, these are binary random variables. There's some probability that the population says they like cats, and there's some probability that the population says they want to do more board work in their numerical algebraic geometry class. Okay. So P and Q are the yeses probabilities. Okay. And a natural question to ask is whether or not these two are independent or not. Independent. Okay. And whether or not we can conclude this at all from our data. And if our data has some small sample size, as it does, because it turns out there's not so many people in a numerical algebraic geometry class, or there's some outliers and stuff, maybe we want to find the closest proportions of all these boxes, which do fit on the variety of two independent binary random variables. Okay. So we are assuming that these are actually independent, and we want to approximate P and Q from our empirical data. That's the question. All right. Great. Okay, so if these really are independent, what is the probability you land in box A?
Would be 1/2, 1/2.
No.
Oh yeah.
P times Q. Probability of P happening, or probability of saying yes to cats, times the probability of saying yes to board, right? Which is only a legitimate thing to do if these random variables are independent. Otherwise, it's not just a product. It's like some extra stuff. Okay. All right. So what is the probability of landing in B?
So that would be P times 1 minus Q.
1 minus P times Q.
Oh yeah, there.
Yeah.
Okay.
This is P times 1 minus Q. 1 minus P. Q. Good. So if somebody gives me a P and Q, I can cook up this map. And it's going from two binary random variables to the joint probability distribution. Okay, so there's a couple of ways to kind of assess whether or not this data lives on the variety, which is the image of this map. So this is a map. So it's really going from 0, 1 cross 0, 1 into, I guess, 0. Let's see, delta. Here, delta 4. The coordinates to this space. And so now what is delta 4? Delta 4 is a set of all ij such that x11 plus x12 plus x21 plus x22. Good. Why? Because all these probabilities gotta add up. You know that this lands in a particular hyperplane. Actually, let's also ask that all the xij's are greater than or equal to 0. Negative probabilities don't make sense. This is known as the probability simplex in algebraic statistics. Okay. I'm going to define M for model, specifically the independence model, is the Zariski closure of the image of this thing. Okay, so this image of this thing really is landing in some simplex, but you can look at the smallest algebraic variety containing that set, and that is going to be called the independence model. Okay. So if we got this data, then the best inference we can make as far as what the empirical probabilities on the joint distribution are is, well, we're just going to divide all of this by the sample size. It's going to give us like some probabilities. That's going to be our best guess for probabilities. If another day there's another numerical algebraic geometry class, and people's answers are governed by these probabilities. So 4, 5, 6, 7, 8. Oh, that's really good that we have 8 answers. That makes our life so much easier. Awesome. By the way, so we're just scaling so that we actually land in this probability. So now for my cartoon. That's my cartoon in simplex, just a triangle. Okay, whatever. There's some set inside here, which is the image of this map. And now we have some point. Is this looking familiar? We have a point that we've gathered from data. And we want to know which point on our model best explains our data. We want a joint distribution which is induced from 2 independent binary variables, which best explain their. And at first glance, especially since I just talked about Euclidean distance degree, you might think that best really corresponds to distance here. But there's a different statistical measurement of best. And that's the likelihood. And now I gotta come up with this. Off the top of my head, I did not got this. So x11, let's call that the probability of being here, the true probability, if these were independent. So we saw that happen 4 times. Right, and each of you is an independent choice. we saw x12 happen once. x21 happened once. And x22 happened 2 times. Okay. Good. So this is the likelihood of observing this data. Okay. And in general, the likelihood P1 it's really this monomial is the likelihood of seeing something happen. So we want to find the x's which maximize this likelihood. But we know that the x's have to come from these p's, come from the image of this map. So we're really looking at something like dq to the u1, 1 minus p q to the u2, u1 minus q, u3. Q time, sorry, 1 minus p, 1 minus q. Want maximize. Okay, well, this is a big problem because these aren't polynomial equations in the parameters. Our data is actually showing up in the numerator, or sorry, in the exponent. Okay, so a priori, not in algebraic geometry then. Okay, data is showing up in exponent. That's bad. Log is monotonic. Monotonic. Okay. And so if I want to maximize some function, I might as well maximize the logarithm. And if I take the logarithm of this, so this is L, log of L is polynomial. Called the log likelihood function. And then with the set of the optimization discussion, you can solve this and you can write down questions. And you can either, actually, in fact, there won't even be any constraints here because P and Q can really be anything. So you're really just doing a calculus problem actually at this point. You're trying to optimize a function. And however, there is an explicit equation for this. Okay. Two explicit equations. And so if somebody just gave you that, and you had some model like that, and then you tried to do this, then you would have some constraints. Okay. And if you work it out, which I don't want to do live because I really didn't prep the algebraic statistics today, you get that. So you can take marginals, you add them this way. So 5 people said yes to board and 3 people said no to board. And 5 people said yes to cats. And 3 people said no to cats. And so you guess that P is 5/3, sorry, P is 5/8, and P actually is also 5/8. So this is actually the best guess for what P and Q are the marginals here. Okay. In other words, this optimization problem only has one critical point. So you can exactly identify what your best guess is, and it's the marginals, which is totally what you guess, by the way. You really track with your intuition. If I gave you this down, like, so like, what's the probability people like cats? You would guess this. Okay, and I don't want to work it out. You can. Okay, so that is yeah, so that is kind of an intro to a world called algebraic statistics, where optimization problems come up a lot. And even if the model isn't clearly parameterized or something, you can still ask the same question, which is I have some variety, and I want to maximize this function, where the parameters are the exponents, so I take logarithm, and it's essentially the question of the critical points of a monomial with respect to a variety. Okay.
Sorry, this might be a bit off topic, but like that thing looks really like some toric, no, not toric, tropical variety or something. Right?
Because it took log of something?
Yeah. Like this is really living in a tropical land. Like if we study this function, the roots of this guy, wouldn't that be similar to that? So if we take a variety.
So I think so I think your intuition's great. So with tropical stuff, you're taking the coordinate wise logarithm of the geometry.
Oh, okay.
Here, this is log applied to some algebraic thing. So it's totally right to see log in an algebraic geometry class and think tropical stuff. And there are lots of tropical connections with algebraic statistics, lots of matroid connections. But I don't think this is the part of the board where it's happening. I could be totally wrong.
No, but yeah, just wanted to throw that out, just to see that if it made sense. Thanks.
Yeah. So Fields medalist Juna has stuff about the maximum likelihood degree. And you can Google that and check that out. So maximum likelihood degree is, of course, the generic number of critical points to this optimization problem. In the same way that the Euclidean distance degree is the generic number of critical points to the optimization of problem of distance to a generic point. These are important natural numbers associated with varieties. Okay. What else? Any questions? Do you want to do a little bit of computation? Yeah. Okay. I'll pause the recording, get this computation set up, and we'll continue. Okay, I'm going to share my screen here. Yeah, sure. Might as well do the whole thing. Boink. There we go. Okay. Well, what do we want to do? Let's let me open some GeoGebra, just because it's the quickest way I can draw curves and things like this. And let's get a curve going. Let's do a quartic. So x to the fourth plus 3 times x squared times y minus y cubed plus x times y equals 0. Oh, nice. That one looks good. You don't always get a good one, Okay, but this looks rather nice. Blue, thick, good. Okay. We're gonna pick a generic point. So the way you pick a generic point in GeoGebra is you just go like this and then he stops. Okay, that's a generic point. All right. Let's find the closest points on this variety to that point. How's this? Let's do that. Okie doke. F is x to the fourth plus 3x squared times y plus x times y minus y cubed. Oh. What the heck is x and y? Okay, as long as I got x and y here, I'm gonna need some lambdas. Yeah. How many lambdas? Probably 2. All right, now let's try this again. And maybe it's best to write this as a list just to stay consistent with the lecture. You know, because you can do this for higher codimension stuff, right? Like you can have some curve in 3-dimensional space or something. Okay, so U is, okay, who's got good eyes? 1.85627. Come on, 1.74636. Which means the function I'm trying to find the critical points of is t equals this for this. Is this that's the square distance to U. Agreed? Agreed? Good. Okay. Okay. So there's the gradient of G. Okay, and grad F is going to be differentiate F. What? Okay, I probably only need 1 lambda, yeah? Because all I'm asking for is that grad G is equal to lambda 1 times, no, oops, grad. And if along with that, I add this equation, then I make a polynomial system out of it. And I tell it that the parameters is lambda 1. Then I have, uh-oh, what's going wrong? Oops. Sorry, everybody. Okay. I forgot to put in the parameters. G should depend on the parameters U1 and U2. My choice of U1 and U2 is one particular parameter value, of course. Okay, so we still need grad G. That's grad F. Grad G. Great. And now we need this system, but the parameters aren't lambda. Lambda was one of our variables, silly Taylor. Okay. Our parameters are U1 and U2. 3 equations, 3 variables, 2 parameters. Okay. That's our Euclidean distance system. And we can solve the Euclidean distance system for target parameters. Just random. Anybody got a guess of how many solutions we're gonna get? Let's make an error here. Because I want to just back up, but I don't want to lose this. Oh my gosh, no. What has happened? Okay, did a really wild thing. Okay. Good. So let's take a look at our ED system. Okay. Who wants to take a guess of how many solutions there are? Give me a bound, maybe. What's the degree of the first polynomial in x, y, and lambda? Somebody said 24. We got a 4 times a 4 times a 4. 4 times a 3.
Then it's me. But that's what-
So the first polynomial has degree 4 because there's an x cubed times lambda 1.
Oh,
The second polynomial has degree 3. It is a y squared times lambda 1 is the largest. So that's 4 times 3, that's 12. And the final one has degree 4. So bounded by 48. Yeah. So Bézier number of ED system, I think. Let's check. Check if you can even do this for parameterized systems or not. Yeah, 48. Great. How about the BKK system? Will that work? No. It's volume.
they will construct a star system if it is not working. Okay.
So far, we've computed that the Bézier bound. Oops, sorry. Bézier number is 48. Mixed volume is 11. Okay. So we expect at most 11 solutions in the torus. Okay. Okay. So now let's solve. Without this goofy stuff at the end, yeah? So this is just solving over just random complex points. It's like essentially a meaningless computation in the context of interpreting it as like nearest point stuff right now. But it's going to form the start system for the parameter homotopy. Okay. And of course, as you all know, working with Julia, the first time running things always takes a little bit longer. I just realized I actually want to keep track of the start parameters too, so let's do it again. Like that. Okay, good. It tracked 13 paths, and 11 of them were non-singular solutions. Okay. There is a way to turn the BKK theorem so that it counts solutions not just in the torus, but in affine space. The way you do that is you include a constant in every polynomial, and then you compute the mixed volume of that. That's what this 13 is. Okay, so it's not the 48, it's not the 11, it's something in between. And that's what the 13 is. Okay, but there are 11 non-singular solutions. Great, so now I want to solve this system with start solutions S1, start parameters P1, target parameters will be 1.8562 7, 1.746369. Okay, so now I'm taking my generic solution set that I computed by doing a polyhedral homotopy, resulting in 11 solutions. And I'm taking that and I'm tracking them via a parameter homotopy to the parameters that are in my GeoGebra picture here. Okay. I can ask for the real solutions, and here they are. That last coordinate, of course, is just the lambda, so we're not going to plot that at all. But we'll take the other two, Control Shift C, put it over here, Control V. Uh-oh. Wow. What? Oh, that's a problem. Is this the same thing as the one that I wrote down? X to the fourth plus 3x squared y plus xy minus y cubed. Ah, wait a second. Lambda came first. There we go. So always be careful about the order of your variables. I assumed that the first two variables were x and y. They weren't. They were lambda and x. That is a thing that happens a lot. Okay, but great. Like this is all part of it. Because you either find this out with me or you find this out alone. But there's a point instead. Let's see if we can see this one better. Yeah, there it is. Boom. Big, red, boom. Line segment. That's perpendicular, okay? See that? So let's get all of them in. If you're super savvy with Julia, you know how to make all these plots super quick just there. But I'm a little scrappy, so. There's this great function here called copy visual style where I click the red one and I click all the other ones. All look like it. Okay, and then just like in calculus, what do you do after you get the critical points? You evaluate the function you're interested in optimizing at each. Make sense? Yeah, so we got 7 real solutions, 11 non-real solutions. Here they are. Equations work. Yeah, we do tangents here. Whoa, I hate that. Never mind. Okay, great. So the winner by visual inspection is F here. Okay. Any questions? Okay. Is anybody interested in seeing anything else in particular? Any questions about Julia and homotopy continuation that you've been bumping into in the homework? With this situation? So we want to try to solve this optimization problem? Sure. Okay, so let's take, yeah, I'd really like to do that offline. Yeah.
It's okay.
Yeah, we'll skip this for now.
It's fine.
Thanks. I have some slides I can post from my computer algebra class. That works out some examples of maximum likelihood problems like this. Okay. I don't think there's anything else I would like to show you here. think that's it, everybody. So next, actually, no, I know what I'll show you. Okay. We're gonna anchor next week, which is monodromy. Okay. Going back. Let's cook up Old Faithful here. And let's solve the Bezout instance, which is 1, 0, -1. Okay, we got 2 real solutions. Yep, checks out. 1 and -1. That is the most difficult way to solve this system. Okay. Good. So now, if I choose just a random complex pair or triple, the homotopy paths from this start system to that target system will be smooth. There won't be any path crossing. There won't be any solutions colliding together. Because with probability 1, I'm not on this exceptional set, which is comprised of the discriminant, b squared minus 4ac, along with a equals 0, this hyperplane. So I could go from P1 to P2, which would be 1. Okay, so where I really want to go is P3, which is 1, 0, 1, right? So this has solutions which are plus and minus the imaginary unit. Okay. But I can't go directly there, right? Because if I go directly from a quadratic equation, which has 2 real solutions, directly over the real locus to a quadratic equation which has 2 complex solutions, then somewhere along the way, those 2 real solutions will have to collide, right? Because that's the only way to jump from having 2 points on the real axis to having 2 points not on the real axis. You can't wiggle off like this because then you don't have conjugate pair solutions, right? So this is a feature of these exceptional sets that I keep drawing, is that on the blackboard, you see that the parameter space gets busted into a bunch of chambers. Okay, and that is because a real manifold, if you take the complement of a codimension 1 submanifold, it disconnects the space. Okay, so you get little components, which are these chambers you see in all the pictures I keep drawing. Or for example, in my background on my computer, actually, this is probably the best thing to show you. Okay, you get these chambers, they're all colored, right? And you see here, there's 5 solutions. 1 is real and 2 are complex conjugate pairs. That's what the blue and red mean. And as you cross from this chamber to this chamber, as you go over, the discriminant is when you have these 2 conjugate pairs, complex conjugates coming together, getting a point which has multiplicity and then splitting apart and becoming real. Okay, so that's how this looks like over the reals. You're seeing a real picture here. Right? But it's really crucial to remember that this totally changes when you work over the complex numbers. Because now your parameter space is some n-dimensional complex space. But this exceptional set is an n-1 dimensional complex manifold. So it's codimension 1 over the complex numbers, which is codimension 2 over the real numbers. Because the complex numbers can be thought of as a 2-dimensional real space. So your real codimension 2. And these homotopy paths are real dimension 1. And that's why you're missing the bad locus all the time. So in order to jump over the discriminant, which is this parabola in the space of coefficients of a univariate quadratic, I'm going to go through some complex point. Okay, I'll keep that 0 and I'll make this like, you know, that. Okay. And so S2 will be solve F. S1 are my start solutions. Start parameters equals P1. Target parameters equals P2. Great, totally worked. I got them. Solutions. Okay. And now I can solve S3 by going from S2 to start parameters at P2 to target parameters at P3. Ta-da! Minus imaginary unit and plus imaginary unit. Yay! Again, kind of a ridiculous way to get there. I started with the Bezier. And then instead of just going straight there, by the way, no gamma trick, just straight there would have been a problem. I jump to some random complex space and I come back down into the real locus. And that gets me off the hook. Because then each of those line segments are generic line segments. Okay, but now I'm going to do something interesting. What was my P2? It was that. P4 is going to be its conjugate. Minus. Okay. So the idea here is going to go from P1 to P2 to P3 to P4, but then back to P1. So this is an even worse way to find the solutions to x squared minus 1. I'm going to start with the start system, x squared minus 1, find the solutions, and then do this ridiculous loop and come back to where I started. Okay. So great. So S4 will be solve F starting at S3, start parameters equals P3, target parameters equals P4. Okay. And then S1 new, we solve F. S4, start parameters equals P4. P1. Good. So this is the same solutions, right? -1 and 1. Agreed? Okay. Well, maybe that's just a numerical error. Let's check. Let's check. Let's remind ourselves what solutions of S1. It's the same set, but they're in a different order. Okay. So look, all of these paths are completely avoiding the exceptional set, right? And so there's no path crossing, nothing funny like that. We're just tracking these things. But eventually we're going around our parameter space and we're coming back. And of course, as you come back, you must also still have the solutions computed. Although there's no promise that they will come to you in the same order. Okay. In other words, if I had only known the solution 1 as a solution to x squared minus 1, and I followed the same path, I would go in a loop, and I would end up at negative. We have already seen this. This was the Cauchy endgame, right? We are essentially doing the Cauchy endgame. We're stopping before we hit t equals 0, and then we're going in a loop, but instead of going in a circle this time, we're going in a diamond. Up to the complex space, back down to the other side, down to the complex space, and back up to where we started. Okay. This phenomenon of solutions permuting as you run around the parameter space and come home is called monodromy. And it may seem pretty innocent at first, like not so much interesting stuff maybe is going on. I don't really see how this helps me solve polynomial systems at all, or understand them, or what have you. But this phenomenon is now, I would say, the #1 way people solve large polynomial systems. So you can use monodromy to actually solve systems. And that's gonna be the topic of, I think, the next 2 weeks. Let me double check the schedule. Yeah, 2 weeks of monitoring. 3 weeks of witness sets. 1 week of certifying these numerical results. Okay. So I think that's class. Sorry I didn't have a more extensive computer session today. But I'll see you next week for what's probably my favorite topic in this course. So thanks.